Okay, great. Can you hear me okay?
Yes.
Okay, great. I want to start off by, of course, thanking the organizers for putting together this wonderful meeting. I love the New England Strings meeting, and I try to go every year that I can. And it's an honor to be invited to speak. And I just was thinking about the last time I spoke at the New England Strings meeting, which was back in 2014. And I was thinking about that talk because that talk was the one where it was based on a paper I wrote with Albion and Mukun and Veronica, where we introduced the term entanglement wedge. So it's certainly nice to see that term that continues to have a life of its own now. Today I'm not going to be I will mention entanglement wedges. This talk will be about holographic entanglement, not mostly about entanglement wedges, but I will mention them. It will be about this idea of bit threads that I've been talking about a lot for the last several years. Bit threads are a way of thinking about holographic entanglement and the Ryutakyanagi formula. In their simplest incarnation, they are a way of thinking about or calculating the entanglement entropy of a region in a holographic field theory, an alternative to the minimal surface prescription that's equivalent. So an alternative formulation, it's equivalent to the minimal surface prescription. And it sort of seems to suggest the idea that because the threads, as I'll explain, as I'll review, connect pairs of boundary points, that somehow bipartite entanglement is privileged. And I want to know to what extent that's actually true, or to what extent that's required by bit threads. Because if you're just calculating the entropy of a single region, then it's sort of, by definition, there's just the region and its complement, and there's only bipartite entanglement if that's the decomposition you've done of the boundary. So in order to explore this further, I want to ask what happens with the bit threads when you have more than one, or when you've divided it into more than two boundary regions. So as a warm-up, we'll do three boundary regions, then build up to 4. That'll be very exciting because at 4 we get to prove a theorem, which is this MMI inequality, and try to understand what that inequality is about. And then I'll briefly discuss higher inequalities, properties of holographic entanglement, and then move in a couple of directions. So one is there's a story about entanglement wedge cross sections and field theoretic quantities like entanglement of purification and reflected entropy. And I want to ask how you can understand those from the point of view of bit threads. And then if there's time, we'll see. I want to just loop back around to this question of whether there's a sense in which whether bit threads do indeed suggest that in holographic states, bipartite entanglement is privileged over multipartite entanglement. And there, I think, we need to be very, very careful about, exactly what we mean. So, okay. And let me just say that I welcome being interrupted with questions in the middle of the talk. Okay, so I'll just, I've given a lot of talks on bit threads, so I'm just going to do bare bones review here. But let me start by saying that in this talk, I'm going to limit myself. So unlike the previous talks, which have all been about quantum effects and so on, which are obviously very interesting and important, here I'm just going to do classical Einstein gravity and also a static bulk spacetime, so I can talk about the original Ryutakyanagi formula as opposed to HRT covariant formula. And it's very interesting to relax each of those restrictions. And if people have questions, I'm happy to talk about what happens when you go beyond Einstein gravity, when you go beyond the classical limit when you talk about time-dependent spacetimes. But that's not the main point of this talk. Another restriction is that I'll assume that I have a pure state, and that is purely for essentially notational convenience. I think it's true that any mixed state that has a good holographic description admits a good holographic purification, like a thermal field double type of description. So it's just more convenient to talk about pure states. Okay, so we're in a setting where we can apply Ryuta-Yanagi formula, and here it is at the bottom, we just have a mathematical rewriting of this formula in terms of bit threads. So a thread is a one-dimensional object. In this talk, it'll be unoriented. I mean, one can keep track of orientations, but I don't need to. So in the bulk, this is the picture you're seeing, and all the pictures you'll see are a time slice of a static or time reflection symmetric space-time. So I'm not talking about the time direction. Again, I'm happy to discuss the generalization beyond that if people are interested in it, but it's more complicated. Anyway, so they are these one-dimensional objects in the bulk, which are only allowed to end on the boundary, and they have a certain thickness, a Planckian thickness, which bounds their density. And that bound is designed to reproduce the Ryuta-Yanagi formula. So it's put in there to get RT out. And I use this notation where the number of threads in some given configuration. So these two rules, of course, allow many possible configurations, and then including, for example, a configuration with no bit threads at all. That would be perfectly allowed. But the statement is that the maximum number you can have connecting A to its complement is, which I denote by this n sub A bar, is equal to the minimal surface area. So this equality here is by virtue of a theorem in Riemannian geometry called Maxwell-Min-Cut theorem. And I just normally when I give talks on bit threads, I just leave it at that. But since I'm going to be generalizing the theorem, and also because the proof is rather beautiful, I just want to say a few words about the proof. Of course, intuitively, it's just that you keep adding threads until you hit this bound somewhere, and the place where you hit the density bound first is on the minimal surface, and then that's why the maximum number of threads is equal to the area of the minimal surface. So it's quite an intuitive. It's not intended to be any kind of surprising statement. But how do you prove such a thing? Well, basically, it's in 3 steps. So the first step is to rewrite this problem of maximizing the number of threads as a convex problem. So you write it in terms of some vector field, and then it's maximizing a convex functional over a convex set. And those are sort of, that's a magical category of optimization problems. There's a huge amount of things you can prove about them. And one of the things you can prove about them is this strong duality relation, where you rewrite it as a minimization convex problem. So the minimization problem is the following one, where so now you forget about threads, okay, but there's some function lambda in the bulk, non-negative function, and you should think of that function as being some kind of obstacle, which is kind of create a barrier between A and A complement. So you're so we've already had one Trump reference in this conference. Time for a second one. So you want to build a wall separating A and A complement, and the wall should be such that anyone who tries to go from A to A complement goes through a total amount of barrier. In other words, an integral of lambda of at least 1. Okay, and then if you think about the solution to that problem, I mean, obviously you're going to put all your resources, if you're trying to minimize the total amount of lambda, just on the minimal surface. So that's the solution. It's just a delta function on the minimal surface, and then by this strong duality, which says that this convex problem is equivalent to this. You find that the maximum number of threads is equal to that area. So I think every step in the proof is, pretty straightforward, except for the strong duality, and that's kind of the magic part, where you just refer to this powerful theorem that relates equivalent convex optimization problems. Okay, so that's the math. What about the physics? Well, I mean, I've already argued in many places that this thread picture sort of offers conceptual advantages over the minimal surface in terms of thinking about phase transitions and quantities like mutual information and all. Come back around to some of that later in the talk, but at least at a crude level, at the level of accounting, since the number of threads equals the entropy, and the entropy equals the number of bell pairs in a distillation, it seems natural that to have the idea that each thread represents one of the bell pairs in a distillation of the entanglement between A and A bar. Okay. And I want to kind of push that idea and ask, to what extent we should take it seriously. Yeah, other ideas have been put forward about how you should think about bit threads in terms of the quantum error correction story, and Horacio Cassini and collaborators have explained that they should be thought of in terms of something called intertwiners from an algebraic quantum field theory point of view. But since I don't really understand that idea, I'm not going to discuss it. Okay, so but I just want to now ask a very down-to-earth question, a mathematical question, which is if I instead of dividing the boundary into 2 regions, I divide the boundary into 3 regions, then how many threads can I have connecting the 3 regions to each other? Okay, so well, the first observation is just that so now I have some threads connecting A to B, some connecting A to C and B to C, and of course, in any thread configuration, the number connecting A to its complement is bounded above by S of A, by this, again, by this relation. And so I have some inequalities that bound the number connecting A to B plus the number connecting A to C, et cetera. Okay, so I have these 3 inequalities. And I also know that I can saturate any one of them by that Maxwell min-cut theorem. But the surprise is that actually you can saturate all 3 of them simultaneously. So there's a single thread configuration that calculates simultaneously the entropy of all 3 of these regions. That's an old theorem from network theory, but to prove it in the continuum, we developed a new, well, we adapted this technique, this convex optimization technique. And so let me just run through that. So it's very similar. You write down a convex program which maximizes the total number of threads, and then you show that that's strongly dual to again, this sort of barrier building problem where now you want the distance or the amount of barrier between A and B to be at least 1, between A and C to be at least 1, and between B and C to be at least 1. Now I'll just pause for a second and so people can think about what the solution to this problem is. What's the optimal way of building your walls to make sure that to go from any country to any other country has a difficulty of at least 1. So the answer is that you build a wall of height 1/2 on the minimal surface connecting each of these. So you have a half delta function on the A minimal surface, half delta function on the B one, and half delta function on the C one. Okay, and then that shows that the maximum total number of threads is equal to half of the sum of these entropies, and that implies that all 3 of these inequalities are saturated. So that's an interesting fact about threads, that you can calculate the entropies of any 3 regions with a single thread configuration. Of course, again, let me emphasize, I mean, if I made a different choice of 3 regions, it would be a different thread configuration. That's always true with threads. Okay. And this theorem generalizes to any number of regions by exactly the same logic. So let's go to 4. And again, so now I'm not going to draw a picture like this one. I'm just going to, here are my 4 regions, A, B, C,
Sorry,
D.
Matt,
Yeah.
I'm not following something here.
Okay.
So if you have a half times the delta function on MA, then why isn't the integral from A to C a half?
Because you have to go through 2 barriers.
Oh, I see. Good, thanks. Yeah.
Yeah, thank you. I should have said that. So yeah, that's why it solves the constraint, because to go from A to C, you have to cross 2 walls. Each one is height a half. Thanks. So and you can show, I mean, if it's not totally obvious that that's the optimum, if you think about it, it is, and you can prove it. Right. So getting back to 4, so we have some numbers between A and B, A and C, et cetera, et cetera. And you can saturate all 4 of these. These originally would be, a priori would be inequalities. You can saturate them all simultaneously, and that's great. However, where things are a little more interesting for 4 regions is that now we have composite regions like AB. So here we have AB, for 3 regions we have AB, but of course C has the same entropy as AB. This is where it's just convenient to be working in the notation and of pure states. Because then I can make the statement that the entropy of C equals the entropy of AB. And so it's not independent. But the entropy of down here, when I have 4 regions, A, B, C, and D, the entropy of AB is equal to the entropy of CD, but it's independent of the single region entropies. Okay, and the theorem does not tell you that you can saturate those. So there's no thread configuration that calculates not just all 4 of these, but also S of AB, S of AC, and S of AD. In fact, yeah, you can definitely show that there, in general, there does not exist, there cannot exist such a thread configuration. Okay, so composite regions are not necessarily saturated, but of course you have the inequality that the entropy of AB bounds above for any thread configuration, the number connecting AB to its complement, which is CD. So you write all these things out, and then you add them up, and you get this inequality. Okay, so this inequality here is what I just proved to you. And this inequality is a fact about holographic entanglement entropies. It's a fact about Ryu-Takenagi formula, and it's a fact that was previously known. It was proven some years ago by Patrick and Alex and myself, and it goes by the name MMI, which stands for Monogamy of Mutual Information. Because if you write it in terms of the mutual information, it's it looks like what they call a monogamy relation in quantum information theory. That's not important for the rest of the talk. What's interesting about this inequality is that, unlike, let's say, subadditivity, strong subadditivity, this inequality is not a property of general quantum states. So this inequality does not constitute any kind of a consistency check for Ryu-Takenagi. Rather, it's a new prediction about holographic states from Ryu-Takenagi that they obey this inequality, which is not true for general quantum states. And it's easy to find counterexample. The simplest one is a 4-party GHZ state, just an equal superposition of 0, 0, 0, 0, 1, 1, 1, 1. You can convince yourself that it violates this inequality. So it's saying that holographic states are not like that. But it's never been really clear, sort of a little more concretely, what it is about holographic states that that makes this property hold. Okay. And it's nice to have a new proof. So the previous proof was, of course, based on cutting and pasting minimal surfaces, and said nothing about, gave no clue conceptually about what the meaning of this inequality is. And bit threads may give such a clue. So I'll talk about that later in the talk if I have time. and I should mention that there's so the proof I just gave you is non-constructive because it uses the magical step of appealing to strong duality. So Veronica has a different proof which is more constructive, although more limited in scope. And then if you want to see pretty pictures of actual thread configurations that realize these, that do these saturations and calculate these quantities, this paper by Cesar, Jan, and Juan has very nice constructions. Okay, maybe I'll actually pause to see if there's any other questions at this stage. Oops. Okay. So this, it turns out that this inequality is just the simplest of an infinite family of inequalities for more than 4 regions that are obeyed by Ryutake and and it's more challenging to understand those in terms of bit threads. So I just want to give a status update about that. So so here, if we start having more regions, then there's an important concept that comes into play, which is whether sets of regions partially overlap, and that's called crossing. So, for example, A, B, and BC partially overlap, so they cross, but these ones that I wrote here, some are nested inside others, some are disjoint from others, but they don't partially overlap. And that's a big difference in terms of the bit threads. So what we can prove is that assuming you have no crossing, then you can do this kind of saturation of all simultaneous saturation of all of the different regions, elementary and composite, as long as the composite ones are not crossing. Okay, and we can prove a stronger region, a stronger result, which proves a conjecture that Veronica made, that actually you can make the bundles. So you in such a bit thread configuration, you can make the bundle of threads that connects any pair of regions not overlap the bundle connecting any other pair. So that the AC bundle would not overlap the AD bundle or the BC bundle, etc. Okay, so unfortunately, or whatever, whether fortunately or not, it's a fact that when you have crossing, then you can show that there does not exist a thread configuration. Okay, so you cannot make a single thread configuration that calculates the entropy of both AB and BC because they cross. And what's interesting about that statement is that this is the first place where you see a divergence between the structure of threads or flows on Riemannian manifold from the structure on graph. So far we've been guided by the mathematics of flows and cuts on graphs, which is a very mathematically well-developed subject. And there's a theorem that you can find the analog of a thread configuration on a graph with crossing regions under certain circumstances. And it's not true in the continuum, okay? And that's interesting because the higher entropy cone inequalities actually do have crossing regions. So, so the next simplest one after MMI is this inequality for 5 regions, which is called the 5-party dihedral inequality. And if you look on the right-hand side, I mean, obviously it has lots of crossing. Okay, and the strategy for proving these inequalities using threads is always to find, or has so far been to find a single thread configuration that simultaneously calculates every term on the right-hand side and bounds every term on the left-hand side, and then you're golden. But you can't do it with these inequalities. So you're going to need something more complicated. Okay, and that's kind of the state of the art. that. And you know, these inequalities have been known for a while, and we just have no idea what they mean or whether they're just random. I mean, whether they reflect something interesting about the entanglement structure of holographic states. You know, if so, we don't really know what, or if they're just kind of, the important thing is RT, and then, you know, these are just sort of random things that follow from RT. Okay, so I'm going to turn my attention now to a slightly different subject, and then I'll come back around to this question of the entanglement structure. But one way to probe the entanglement structure is with more refined quantities than just entropies. So far I've just been talking about entropies, and of course linear combinations of entropies, but you can do more interesting things. And one thing you can do is talk about more sophisticated quantities. And that's what people have been doing recently, and throwing out conjectures left and right, some of which are hopefully true. One sort of nice, clearly nice generalization of Ryutakinagi is to look at the cross-section of the entanglement wedge shared by two regions. So I look at the joint entanglement wedge of AB, and if A and B are large enough relative to their separation, then that entanglement wedge will be a bridge connecting A to B, and then I can ask what is the minimal cross-section of that bridge. That seems like a very natural geometrical quantity, so maybe it has a dual, and so people have been conjecturing all kinds of duals for that. And I'm not this is not a review on that subject, and it would take a long time to review all the different proposals that have been made. I think I'll basically, yeah, let me just leave it at that for now. And I just want to say that that is a quantity that you can calculate using bit threads, and you're simply looking at the number of threads connecting A to B within the entanglement wedge. And then you can, these conjectures have various checks which involve properties of these field theory quantities versus geometrical properties of the entanglement wedge cross section. And all of those geometrical properties you can prove using bit threads. And it's pretty straightforward, and I'm not going to go through that. What's more interesting is what happens when you have more than two regions at once. So you have this notion of a multi-region cross section, and here there are various generalizations you can make. So from a geometrical point of view, one thing you can ask about is the area of the minimal surface that joins all of the RT surfaces, or that joins all the parts of the RT surface, the shared RT surface here of A, B, and C. Okay, so let me go through that again. So here I have three boundary regions, A, B, and C. I look at their joint entanglement wedge, that's the blue region. One thing I can calculate, which is the dotted line here, is the entanglement wedge cross section separating A from A complement, namely separating A from BC. Okay, and then I have the one separating B from AC and C from AB. But there's a different quantity I can look at, which is the dashed line, and that actually, there you're actually forcing the surface to end on the same points on the three RT surfaces. So that's a reasonable geometrical, I mean, it's not, there's no rule that says that it has to have a meaningful dual in the field theory, but it's been conjectured that it does, and it's this quantity called the multipartite entanglement of purification. And one thing about this quantity is that it, so the definition is here, and it's similar to the definition of entanglement of purification if you're familiar with that. And it's pretty easy to show from the quantum mechanics side that it that this multipartite entanglement of purification is bounded below by the sum of the bipartite entanglement of purifications. And that is also true geometrically. So you can see that because I've added an extra constraint in the definition of this three-way entanglement wedge cross-section, it must be larger than the sum of the dotted ones. Because topologically, they're the same, except that I have the extra constraint. And since I'm doing a minimization, if I add a constraint, it's going to raise the minimum value. Okay, so at least that property, this property is obeyed by EW. Okay. And you can calculate this area with threads. It's a little bit complicated, but it has a nice feature, which is, okay, so you need a different color of thread or species of thread for each boundary region. And these are sort of living on different sheets if you want. So they don't interact in the bulk. So there's no density bound. Each one by itself has the usual density bound, but they don't kind of take up space for each other. Okay. And they can end on the region that you're of interest, like the blue ones can end on the blue boundary, but they can also end on the shared RT surface. But at any point where they end on the shared RT surface, all three species, if it's three in this case, in this picture, have to end at that point. So here I have a blue one ending, then a red one, and a yellow one have to end at the same point. And then what's nice is that when you have such a picture, then you have the threads which end on this on this joint RT surface actually calculate the difference between the multipartite and the sum of the bipartite quantities. I mean, more precisely, they calculate the difference between the area of the dashed line and the area of the dotted ones. So you can speculate that they represent the multipartite part of the multipartite entanglement of purification. In other words, some part of this entanglement of this multipartite entanglement of purification here, which is defined up here, is just due to bipartite entanglement, and some is, and that's the part which is given by this right-hand side, and the difference between the left and right-hand sides would be the sort of truly multipartite part. I mean, that's, you know, again, this is basically just a counting argument. We don't have more evidence for it, but it's an interesting idea. It's sort of natural from the pictures. Okay, any questions before I go on? I have no idea how much time I have left, so.
You started 20 minutes late, so you have about 10 more minutes and 10 minutes for questions.
Okay, great.
Mm-hmm.
So then I will have time to talk about bipartite dominance. This is an idea or a question that's raised by this theorem that I mentioned before, which is basically the question is kind of how literally you should take the picture. Okay. Okay, so let's go back to the case of two regions. And as I said, as far as the counting is concerned, the number of threads is equal to the number of bell pairs after an entanglement distillation. And that's just because it's by design equal to the entropies. And that's, by the way, also equal to half the mutual information. So fine, I mean, that's kind of a truism. With three regions, what you notice is that if you calculate the mutual information between A and B, half the mutual information is actually equal to the number of threads connecting A to B. And so that suggests that this is actually a picture of a three-way distillation into bell pairs. Okay. Now, in the case above, the fact that you can do a distillation into bell pairs and the number of bell pairs is equal to the entropy is, as I said, is basically a truism. But for three regions, in general, for a three-party quantum state, you cannot do a distillation into bell pairs because it might have tripartite entanglement. So if this is true, then it would be saying that the state only contains bipartite and no tripartite entanglement, which is a pretty strong statement about the nature of the state. Okay, so I want to ask the question of whether, whether we should take that concept seriously. It would be saying that actually holographic states are in some ways very simple. Okay, but first, we have to understand how strong this statement is exactly. It's a little more complicated than it looks at first. So first of all, the claim I would be making here is that you can do a three-party distillation for any choice of A, B, and C. And at first glance, it sounds like the only way that could possibly be doable is if the state originally only contained bell pairs. That is, if you didn't even need to do a distillation, okay? Because I'm saying that if you just chose a completely different A, a completely different B, and a completely different C, you could still do the distillation. And how is that possible no matter what my choice of A, B, and C are? So one way it's possible is, of course, this obvious thing if, like, here's an example with 5 parties and various bell pairs connecting them. Of course, since there's only bipartite entanglement to begin with, it's obvious that when I group these into any 3 groups, they'll still only be bipartite entanglement. But of course, we know that holographic states are not so simple. So are there non-trivial examples of states that look like that? And there are non-trivial examples, and the next simplest is what's called a 4-party perfect tensor. So that's a state on 4 parties that has the property that all of the 2-party mutual informations vanish. And so it's some particular kind of 4-party 4-partite entanglement. And it has the property which you can convince yourself pretty easily that if you take any 2 and group them into 1, then you can do a distillation, in other words, a unitary on that now 1. So CD to split it into C1, C2, such that there's only bipartite entanglement. So it's not the case, this has truly 4-party entanglement, okay? But if I do the grouping, then I can do a distillation that splits it into 2-party, and that's true no matter what groups I make, okay? So what I'm saying is that holographic states would be kind of like that. So, okay, that's fine, but that's kind of a very small toy example. But are there bigger states? Well, yes, the random stabilizer tensor networks, which are kind of toy model of holography, actually also have this property. That when they have some large number of boundary regions, or sorry, boundary vertices, and if you group that large number into 3 sets that you call A, B, and C, then you can do a distillation where the whole thing just falls apart into bell pairs, okay? Okay, so we have toy models of holography that actually look like this, okay? So it's not a ridiculous idea. That doesn't mean it's right. Now it's important to understand that this is not saying that holographic states only have bipartite entanglement. It's a particular statement that when you do the grouping of the boundary into 3 regions, then it falls apart into only bipartite entanglement. What if I do the grouping into 4 regions? Well, then if this is true, it implies that for any 4-region decomposition of the boundary, you have a very special structure, which is that you only have bipartite entanglement among those 4 regions, plus possibly 4-party perfect tensor entanglement. So it's still very restricted. The only type of 4-party entanglement that's allowed, if this statement about 3-party entanglement is true, is 4-party perfect tensor entanglement. Okay, and what's nice about that sort of ansatz for the state is that it explains this MMI inequality. So if you evaluate the left and right hand sides of that MMI inequality on any state of this form, it automatically obeys the inequality. So if it's true, so this hypothesis about entanglement of when you group the boundary into 3 regions, if it's true, implies MMI. So it explains MMI. Okay, so that's just to say that it's motivated. That is certainly not to say that it's correct. And in fact, there's very good arguments that it's not correct. So I think this idea has led to some interesting work that I want to talk about next. But first, let me say something very important, which is that actually this conjecture is actually much vaguer than it looks at first, because I put some wiggle words in here. Up to bulk quantum corrections. So, okay, I can't get it to select what I wanted to select, but that's okay. Up to bulk quantum corrections. So, of course, if you don't, so all of these computations so far are leading order in in G Newton. So so everything here is just sort of Ryu-Takayanagi formula, not including the FLM corrections. And those FLM corrections are absolutely crucial. Of course, you would never get 2-point functions on the boundary if you don't include those FLM corrections. So, so those quantum corrections are definitely there. And the question is, what effect do they have on this bipartite dominance idea? Okay, and that is left unspecified. And there's a lot of room, there's a lot of wiggle room there in the effect of the quantum corrections. Okay, I mean, that's kind of actually where it's interesting, is to ask, well, what does this conjecture even mean in the presence of quantum corrections?
Right.
Okay.
So for example, in the island case, this property will not be true?
Well, at least in the at least in those island cases, so it might be true from the sort of second holography point of view, but it wouldn't be true. It wouldn't be true in the cases where you don't have any classical description or any sort of any description where RT without FLM is valid.
Thank you.
Yeah. Right. So okay. So the question is right. So I hope I've argued that this idea, although it's incredibly constraining for holographic states, is also not completely ridiculous. But to study it more, you need more fine-grained probes of the entanglement, and thankfully we have that now with this whole business of entanglement wedge cross sections. Okay, so let's first put aside the quantum corrections and go with the assumption that this bipartite dominance is exact. And if it's exact, then the mutual information between A and B. So now, yeah, I'm in a situation where I have A, B, and then whatever its complement is. That mutual information must be entirely due to entanglement. Okay, and that fixes the reflected entropy along with, and so I'm going to use the terminology of reflected entropy because I think that's the easiest to understand, and it's the most well motivated of these entanglement wedge cross section conjectures. But many of the statements I make are also valid for example, entanglement and purification. But let's just focus on the reflected entropy. Okay, so if there's no tripartite entanglement between A, B, and C, then I just have some bunch of Bell pairs, half the mutual information number of Bell pairs shared between A and B, and then some other stuff shared between A and C, and some other stuff shared between B and C. So to calculate the reflected entropy, you calculate the reduced density matrix of AB. So now we have this mixed state with these sort of dangling bonds, and the thickness of this line is still half the AB mutual information. Then you reflect it, so you do this canonical doubling of this canonical purification of the state, where you introduce A prime and B prime, and then you still haven't changed this. You still have half the mutual information bell pairs between A and B. Because you've doubled it, you have half the mutual information bell pairs between A prime and B prime. And now you calculate the entropy of AA prime, and you just get the mutual information, half from here and half from here. So with this ansatz, the reflected entropy equals the mutual information. That's another way of saying that so normally the mutual information can be due both to, in a general quantum state, to entanglement and or to classical correlations. We don't really know in holographic states, you know, how much is one or how much is the other. That's not really a well-defined question, but that's the kind of question that these reflected entropy and entanglement of purification quantities help us to understand. Okay, so in this case, we see that if bipartite dominance is exact, in other words, if we ignore quantum corrections, then we get this very simple answer for the reflected entropy. Sadly, this answer for the reflected entropy is wrong, okay? Because you can, under the assumption that the reflected entropy is twice the entanglement wedge cross-section, most of the time, twice the entanglement wedge cross-section is actually larger than the mutual information. And this is a strict inequality. I mean, you can calculate the two sides very easily, and this number is larger than this number. Okay, so I'm usually very bad at following the details of calculations during talks, but I hope that people can see that these three relations are not mutually compatible with each other. So that would seem to kill bipartite dominance, but there's a sort of a way out, possibly, which is that, of course, we ignored the quantum corrections. Every quantity here is at order 1 over G Newton, so a leading order, okay? So you would think that, well, the quantum corrections are just going to change things by order 1. We know the quantum corrections are going to change the mutual information at order 1. So they can't possibly save the day. But there are quantities where quantum corrections sort of jump a level in the G Newton expansion. They don't respect the G Newton expansion, like Renyi entropies famously don't respect the G Newton expansion. Because subleading parts of the wave function get amplified when you calculate a Renyi entropy. So maybe that happens here when you calculate a reflected entropy, which is, after all, nonlinear in the state. You know, there was this step where you square the state. So maybe subleading, exponentially suppressed parts of the state are getting lifted up and are you know, polluting this reflected entropy quantity. So that's a valid question. If basically, if the point is that due to these quantum corrections, this relation is not correct, so this calculation I did here is not correct, then bipartite dominance could be true, okay? So that's a question that Chris and Pratik studied and argued that it's not going to save you because they showed that the reflected entropy is continuous. So basically, it can't be so violently changed by a very small change in the state, where they defined a small change in the state to be one which is small in trace distance. Okay. Now, there's a question about whether the trace distance is correct, and at least is the relevant measure here. And one thing I'll say is that, I mean, I think this is a good argument, but it's not completely airtight, because we do know of cases where these small quantum corrections do lead to a huge trace distance between states. And an example is just if you're sitting right on the mutual information phase transition, where actually the mutual information is 0, not including quantum corrections. And therefore, if the mutual information is strictly 0, the reflected entropy and any other measure of correlation you calculate has to be 0. And yet the reflected entropy, if you're just on one side of the phase transition, is not 0, it's large. And so those quantum corrections must have gotten amplified. Okay, so that's at least one case where small quantum corrections do seem to amplify and lead to a much larger effect than you would expect on the reflected entropy. Whether that's happening here, I don't know. So I'm not saying that this this shows in any way that bipartite dominance is correct, but I think it's very interesting. I think all of these questions kind of highlight our ignorance, our confusion about how to think about these different entanglement measures, especially in these very, very large Hilbert spaces. Okay, I hope some of that was sort of clear, because there were a lot of logical back and forths in that. But anyway, I'll stop here, and I'm happy to take questions.
Great, thank you, Matt. Let's stop. So we could take a couple of questions. So you can just unmute yourself and ask a question, or you can raise your hand, or you can write your question in the chat.
I have a question.
Mm-hmm.
So what happens if you replace bit threads by graphs instead of one manifolds?
Right. Right. It's a great. So if I interpret your question correctly, what you're asking is, if we're trying to represent multipartite entanglement, we should not use just one manifolds. We should use some structure,
something like a Y or or an X or something like that.
Yeah, that allows that. I have not been able to come up with kind of a nice mathematical representation that would allow me to do things like calculate or prove theorems about such things. And that's just a statement about my own limitation. So I think it's a great question. I mean, I will say that if you go back to the four-party case, if you want to ask a question like, how much of this four-party perfect tensor stuff is there? And you want to use, so naively you would think, well, of course, bit threads cannot represent that part. They can only represent this part, the bipartite part. But the bit threads do manage to represent this amount. This amount is equal to the difference between the two sides of the MMI inequality. Which is, oops, where'd it go? So the difference between the two sides is a quantity which is called I3, tripartite information. It's the amount of perfect tensorness in your four-party state. And how do the bit threads represent that? Well, no single thread configuration represents that, but if you look at the number of threads if you look at the space of thread configurations, then you have threads that, pairs of threads that can switch off from, let's say, having an AB and a CD connection to having an AC and a BD connection. And the number of thread pairs that switch off is this amount of perfect tensorness, is this sort of number of four-party perfect tensors present in the state. So if you just go, so what I'm saying is that one way to go beyond this is to go up a level by, instead of talking about any individual configuration, talk about the space of configurations. And when you go up a level like that, then you can see these multipartite structures. So that's one way to do it.
Thanks.
Right. Are there more questions?
Is there any motivation to consider 6-body perfect tensors and so on?
Right. When you get to, I'll give a slightly roundabout answer. The short answer is there is, but they're kind of not going to be enough for what you're going to want to do if you want to generalize this thing I'm saying to more than 4 parties. And the reason is that, so when you go to higher parties, then you talk, the good language is the holographic entropy cone. And that's a convex cone. And the extremal rays of that cone, by definition, are things that positive linear combinations of them fill out the whole cone. And in the four-party case, the Bell pairs and four-party perfect tensors are the extremal rays. And so that's all you need to fill out the whole four-party entropy cone for holographic states. At higher parties, it would have been nice if it had been true that all of the 6-party, 8-party, and so on perfect tensors, fill out the entropy cone for any number. And that's just not true. So you need lots of other states, and it grows very quickly, the number that you need as extremal rays in the entropy cone to fill out the entropy cone. And so yes, you do have to include 6-party perfect tensors, but you've also got to include like a ton of other crap. And so there isn't kind of a clean, no one knows a clean description at more than about 5 parties of the entropy cone. Something that would be a nice analog of what we have here.
Thank you.
More questions, please?
Yes, hi. I was wondering if you could comment on what happens if you keep track of directed bit threads.
Well, it seems, yeah, it's not useful for anything I've talked about here. Of course, you can convert, the point here is that in a configuration like this one, if you insist that when you calculate S of A, all the threads leave A and enter A complement, which is the kind of language that I used in like my first paper on bit threads with Mike Friedman. It's all oriented threads and it's all the number of threads leaving A. That's the language that's used there. And of course you can do that. You can just put arrows on these so that all these threads are leaving A, but you can't do it consistently. Then the arrows have to switch when you're calculating S of B and switch again when you calculate S of C. So you put some decorations on, but then you have to take them off every time you do something different with this one picture. So that's why I preferred unoriented threads. In the language of flows where you have vector fields and then you can do things like add and subtract vector fields from each other, it's often handy to do that for computing things like conditional entropies. And yeah, so when you represent a thread configuration by vector field, it's intrinsically an oriented configuration.
Okay, thanks.
Okay, maybe one last question, please. There's one raised hand. You can just unmute. Could you please unmute yourself and ask a question? Okay, disappeared. Any more questions? All right, if there are no more questions, let's thank Matt again.
Thank you.
Thank you.